So an elementary matrix is a matrix that comes from the identity matrix where you perform one row operation. So remember, there's three different types of row operations. There's a row switch, there's a scale a row, and then the other one that we use the most is to multiply one row and add it to another and replace that row that we're adding to. And if you have, so an elementary matrix has to be a square matrix because it comes from the identity, and the identity is a square matrix. If an elementary row operation is performed on an m by m matrix A, the resulting matrix can be written as E times A, where E is created by performing the same row operation. So that's the part that I want to show you using Matlab or using some computer program, so that you can find these matrix multiplications, or you can do these matrix multiplications really quickly. And then each elementary matrix E is invertible. We talked about inverses already. That means you can multiply the inverse with something, and then the inverse of that elementary row or elementary matrix is maybe not exactly the same as that matrix, but it's of the same type. So again, three types of row operations, so three types of elementary matrices. All right. And then from here, the best thing to do is to explore these ideas using Matlab, so, or whatever else you want to use. I'm going to use Matlab. So I'm going to pull Matlab out, and let's make up a matrix, and let's call it A, because it's kind of easy to make up matrices here. So A equals, and then I'm going to use square brackets, and I'm just going to use numbers with spaces and then colon or semicolon to give you the next line. That's, I think, one of the easiest way to create matrices. So let's do 1, 2, 3. I think it's 4, 5. I think it's 5, 6, 8, and then 10, 11, 12. Maybe it was 13. I forget. And the nice thing about this is that when you run this, it'll show you the matrix and how it actually looks like. All right. So what we're going to do is we're going to come up with an identity matrix. By the way, a quick way to do an identity matrix in Matlab or something like that is I, like I, capital I. And then I think it's in parentheses 3, so this is going to be a 3 by 3 identity matrix. Not that we're going to use that right now because we're actually going to fill in a matrix. But let's look at the identity matrix. Let's look at a 3 by 3 identity matrix. And let's take a look at your matrix A and ask yourself, what do you want to do with the matrix A to try to do a row reduce? So what is one good elementary row operation we can make on matrix A right now? Yeah? I don't know if I kind of want to save the dividing stuff a little bit later. There might be one that might be easier. So multiply the first row by -5 and add it to the second row. Now, if you've written those functions in Matlab, you can just do that on the identity matrix. But if you haven't, let's just actually create it, and let's name it, because we're going to want to keep track of these elementary row operations. So E for elementary and 1 for the first one. So let's let E1 equal to, now imagine doing that operation. Sebrian said we're going to multiply the first row by -5 and add it to the second row. And how's that going to look like? So 1, 0, 0. What's the second row going to look like? What? Negative 5, 1. So minus 5, 1, and 0. I need semicolons. So your matrix should be 1, 0, 0 for the first row, negative 5, 1, 0 for the second row, and 0, 0, 1. So what you did here is you took the identity and then you multiplied the first row of the identity by negative 5 and added it to the second row, right? So that's what you have. Now, what they're saying in this paragraph here, this is actually just one sentence, is that if an elementary row operation is performed on an m by m matrix, it's the same as multiplying this by an elementary matrix on the left side. So what we're saying here, or what they're saying, is that if we multiply E1 times A, we should get the same effect as if we took A and we did that particular elementary row operation on it. Does that make sense? So if we run it, we see that the resulting matrix it still has a 1, 2, 3 up on top and a 10, 11, 12 down in the bottom, but now the middle row, it's like having multiplied the first row by negative 5 and adding it to the second row. Erica? Well, that's a nice thing about doing Matlab is that, let's try it. And yes, it does, because we got a different answer. So remember that commutativity is important and that matrix multiplication is not commutative. Yeah.
Is that always just like a 0, like a 1? Is that like a default thing?
Yeah.
Or is that the reduced row echelon?
No. I mean, eventually, if all the columns are linearly independent, eventually it'll look like that. But before the idea of row reducing it, the identity is just ones and yeah. So I don't want A times E1. I want E1 times A. Right? So we can call that another matrix if you want. I'm just going to call it E1 times A. And what I'm going to do now is I'm going to I want to create another matrix, another elementary matrix, to see if I can eventually row reduce this. Okay. So looking at this new matrix that we just got, what do we need to do to get another 0 down in the first column? Yeah, so what is our new elementary matrix? So if we have this other matrix where we take the identity, again, you have to go back to the identity. You multiply the first row by negative 10 and add it to the third row. Then this is our matrix. Now, if I multiply this by A, I'm gonna make that last spot in the first column 0, but then I would have not accounted for the first elementary matrix that I have. So what I want to do is I want to multiply E2 times the resulting matrix after E1. So I didn't call that anything else. So I'll just say E2 times E1 times A. Okay. Say it again. Always put it on the left. Always multiply on the left side. Yes. Well, it's associative, so technically I can multiply by E2 E2 and E1 first and then A, and it should still work. But whenever you add on another elementary matrix, then you're going to multiply that on the left. Always want A to be on the right. And you can see now that we've gotten rid of that negative 10. And so now this is our matrix. The tricky part about this is that I'm going to start having to deal with fractions and stuff. So all right, so let's do that. Let's switch the order. Because we're practicing elementary matrices. So let's switch the second and third rows. So what elementary matrix will switch the second and third rows? What's my first row? First row is 1, 0, 0, because I'm not going to mess with the first row. What's the second row? And then the third row? Right? So here is my identity where I switch the second and third rows. And then now I'm going to multiply my current matrix, which is E2 times E1 times A. And I'm going to multiply that by E3 on the left side. And then I should have this previous matrix over here where the rows have switched. So now I have a negative 9 in the second row instead of a negative 4. And it seems like that's a nice number to wipe out. So how do I get rid of that negative 9? Divide that row by negative 9, right? Or multiply by 1/9, technically speaking. So let's create another elementary matrix, E4. And what's E4 going to look like? I'll say 1, 0, 0 for the top row. What's the middle row? Negative 1 over 9 and 0. And then the last 0, 0, 1. All right, so this thing is going to start going into fractions, or into decimals, but hopefully when we multiply it, it'll cancel and then it'll undo each other. So I have 1, 0, 0, 0, negative 1/9, 0, and 0, 0, 1. And so I'll take E4, multiply that with the current matrix, which is a product of all these things. By the way, like E1 times A, maybe you can call that A1 if you want, and E2 times E1 times A, you can call that A2 if you want, but I have this string of multiplication because you'll see later that there's going to be something I'm going to want to do with that. All right. Oh, they're still fractions. I mean, they're putting them in decimal form here, but okay, I got a 1 in my pivot position in the second column, so that's good. So big. And then now I want to get rid of the 4, the negative 4, right? So I'm up to my 5th elementary matrix here. So what's my 5th elementary matrix? If I look at that last matrix, I want to get rid of the negative 4. I'm going to multiply what by what and add it to what? What? Yeah. 4 times the second row added to the third. So imagine doing that to the identity matrix. 4 times the second row will give the negative 1 in the second column, or negative 4 in the second column, positive 4 in the second column. and then add it to the third column. So your elementary, our other elementary matrix should look like this. Right? And now let's multiply that to the previous matrix. So that's E5 times E4 times E3 times E2 times E1 times A. It's hard to keep track of this. So now I have zeros. I also have a 1 in the diagonal, so that's great news. I just have a couple more to do to wipe out the others to make this a reduced row echelon form. Say it again. It got lucky. I mean, if we change one of the numbers in A, then it might not work out the same way. So that's good. All right. Can you find the other matrices? How many more matrices do you think we'll need? Probably 2, maybe 3. Right, so we're in E6 now. E6 equals 1 0 0 0 1 0. Uh-oh. Which one? In the first row or second row? Second row, let's change this to yeah, you can probably do that. But then that's that. So if you do 2 of them at the same time, it's not going to be an elementary matrix anymore. Oh, I see. Let's see. So you want to get rid of this first? Let's get rid of that first. So let's make this 1, -2, 0, 0, 1, 0, and 0, 0, 1. So let's do this, getting rid of this 2 here first, making that into a 0. And then so our new matrix would be A6 times A5 times A4 times A3 times A2 times A1 times A. Oh, that's E1. I've been saying A. So it's E6 times E5 times E4 times E3 times E2 times E1 times A. And then hopefully that'll get rid of this. And so now we have to get rid of, so we do have 2 more to go. Yeah. Well, we could have gotten lucky again. So E7 and E8. E7 is going to be, doesn't matter which one. Let's get rid of the first row, third column. That would be a 1, 3 spot. So 1, 0, what is this, a 1? 1, 0, 1, 0, 0, 0, 1. Yep. What? Yeah, because it'll look like 10 or 101. You could put commas, which is another thing that you to add on, and then you don't put the spaces, but this is easier to type. So E7 times E6 times E5 times E4 times E3 times E2 times E1 times A. Got my 4, yeah. Oh, one more. So E8 is equal to what's it equal to? 1, 0, 0. 1, -2, that'll get rid of that. 0, 0, 1. And then E8 times E7 times E5 times E4. Oops, E6, thank you. Yes, success. I don't know. Are you using Matlab? Are you guys using Octave or you get zeros, scientific or engineering notation or whatever? Because these are all whole numbers. They should have been just -0. Yeah.
You were multiplying elementary matrices to an A
Yeah.
to an element or to an identity matrix.
Yeah.
But what I thought elementary matrices you just you don't multiply. You can't just add it to random.
Oh, we're not. So each of these elementary matrices that we have, E1, looks at the identity, and then we did one basic row operation on it. So, like E1 does the
Oh, you multiply by -5.
multiply the first row by -5 and then add it to them. And then one of our elementary matrices, I don't know which one was the swap rows. I forgot which one it was. It wasn't E4, E3, yeah. So E3, we swap rows. So you take the identity and you swap a couple rows, and there's another elementary matrix. Okay? So the other piece of information they have is that each of these elementary matrices is invertible, which means it has an inverse. So I can kind of cheat right now and look at the inverse function in Matlab. So let's take a look at E3. What do you need to do to E3 to get back the identity element? What can I multiply E3 by to get the identity? Yeah? So another row swap. Yeah. So if I do another row swap on E3, then that's going to be the identity. So the identity is itself. Does that make sense? Yeah? No, if I multiply E3 times the identity, then I'm just, anything times the identity is itself. But what I'm trying to say is that if I multiply E3 times E3, right? So if I row swap and then I row swap again, then I'm going to get the identity. So it looks like if I do a row swap, the inverse of the row swap is the exact same thing. So that's an interesting thing to write down, and I'll write it down in our notes. Yeah. The identity for right now. Yeah. So if E is an elementary matrix that does a row swap, then its inverse is itself. Okay? Is that good? So that's the easier one. The next one is that what if we do a scalar? So which one was that? E4? So E4 was a scalar multiplication, and we took the elementary matrix. We said -9 minus 1/9 times the second row. What would be the inverse of this? I'll call it E4 INV. -9. So we're guessing that the inverse of this type of elementary row operation would be another type of element, the same type of elementary row operation, except we're going to multiply by the reciprocal. Instead of multiplying by -1/9, we're going to multiply by -9, the reciprocal. So the key is, or the test is to see what E4 times E4 inverse is. Or E4 inverse times E4, we should get the same answer, right? Because that's supposed to, when we're finding the inverse, then that is commutative to get the identity. So let's see if we can write that in our notes. How can we say that in our notes? So I called E4 inverse or we guessed that E4 inverse is equal to, I guess this is what I typed in. I just put E4 INV, no spaces. But that's just a name we're calling it. Suppose I can do both of them here at the same time. All right, so how do we describe this elementary row operation? So if E is how can we describe this? That scales a row by some constant, then its inverse is the identity, or is a row scale again by 1 over C, by the reciprocal. It has to be in the same row. So multiply row. All right, the last one, which happens to be the most common one, I think almost all the rest of our thing. So what do we need to do? What do we need to multiply this by? So the inverse of E1, so E1 is this thing where we multiply the first row by -5 added to the second row. So how do we get back the identity? What do we need to do to this to get back the identity? E1 inverse. What's E1 inverse going to be? It's another row operation, right? We want to simplify that to have a 0 where the -5 is. So it's another add or multiply a row and then add it to the same row, except you're going to do it with the opposite, the sign switch. You're going to do it instead of -5, you're going to do +5. And just to check, we'll multiply the E5 with its inverse, or what we're assuming its inverse, or E1, sorry. E1 times E1 inverse, and that's the identity. And E1 inverse times E1 is also the identity. So how do we say that? If E is an elementary matrix where you multiply one row by C and add to another row, the inverse is same thing, right? Except we're going to multiply by -C instead of +C. Now let's keep it so that it's like a row addition. So multiply the first, or not the first, multiply the row by -C and add to the other row. So that's how we get the inverse. Okay? So those are elementary matrices. So what we've done, I don't know if you've noticed what we've done here. If we multiply by enough elementary matrices, if we multiply the matrix A by enough elementary matrices, appropriate elementary matrices, then we can get the identity. Is that correct? So you have A, we multiplied it by E1, E2, E3, E4, E whatever, by a series of multiplying by enough elementary matrices. Maybe I should just start with E1 and E2. Well, anyways. So what we're interested in eventually is to find the matrix, the inverse of A, the original matrix A. Okay. And so what we can do is we know that E has inverses, right? All the elementary matrices have inverses. So what we can do is we can multiply both sides on the left side by the inverse of the previous matrix. Actually, I'm going to change my approach here. Let me do it a slightly different way. Pedro. kind of.
So we're just doing them using Matlab.
Yeah, yeah, yeah. Because I want you to see those elementary matrices, and I want you to see what happens when you actually multiply those elementary matrices. Okay. So what I'm going to do instead of my task here, or what I'm interested in, is to find A inverse. And so at first I was going to peel them off one by one, but I'm going to skip that and do things a little bit differently. I'm going to take a look at the elementary row operation, or not the elementary row operation, but the elementary matrices that we've accumulated here. And I know that each one of them has an inverse, right? Each one of them has an inverse. And so if I collect all those elementary matrices, all these elementary matrices also would have an inverse. So let's call this, we want the inverse of EJ times E dot 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 E2 E1. Right? So this thing has an inverse. So imagine if I multiply this by the inverse here and here on the left side of either side of the equation, then the inverses here would cancel out, and then I would have the inverses here times I. Right? Yeah. Yeah, it would be. But since I is the identity, I can multiply that on left or right. So what do we have here? We will have A is equal to oh, wait a minute. Sorry. I just found A. I didn't find the inverse. Um, can't divide. I lost my train of thought. Sorry, guys. So let me backtrack a little bit. I have all these elementary matrices, EJ, all the way up to E2 and E1, and multiplied times A, and that's equal to the identity element. So instead of multiplying both sides, which we might want to do later on, but for right now, since I am interested in finding A inverse, we actually already found A inverse. Yeah, A inverse is exactly these elementary matrices multiplied together. Totally missed that. So that is A inverse equals EJ times E2, E1. All right, so that's interesting. How many E's do we have here in our MATLAB example? 8. So if I take E8 times E7 times E6 times E5 times E4 times E3 times E2 times E1 without the A, then this should be my inverse, right? Actually, if you press the up arrow, you're gonna get your previous command back, right? So I just press the up arrow, and I actually want to call this AINV equals to. So I'll name it something so that I can refer to that, and then I can actually multiply A times AINV to give me the identity. Yeah. So when your program does things, it doesn't do things exactly, and it approximates things. So when it starts approximating things, it'll be off by some minuscule, and in this case, it's probably off by 10 to the negative 25th power or something really small. But it's on the negative side, so it calls it negative. Okay. I think so. All right. So that's our inverse. Our inverse is just all these elementary matrices, and then I can also express A. Turns out this is what I was trying to do initially. Also, A is going to be equal to EJ times dot 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 times E2 E1 to the negative to the inverse. And you know that if you have the inverse of a product is a product of the inverse written in reverse order, right? E1 inverse times E2 inverse times dot 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 times EJ inverse. And you can actually find A to equal to that. Yeah. You can, but again, I is the identity, so it doesn't matter which way you multiply. Yeah. In reverse order, yes. So the inverse of a product, AB inverse equals B inverse A inverse. So this little rule will help us with a string of elementary matrices. The inverse of a product is the product of the inverse in reverse order. So in Matlab, you can actually, so we have A inverse, what AINV again? We got this by multiplying the things, right? In Matlab, you can actually directly find the inverse by doing the INV function, INV parentheses A, which should give you the same result. And in this case, it does. Okay? Yeah. You would say INV. What do you mean? Oh, INV E4. INV open parentheses E4. So we found the inverse of A using the elementary row operations, but we also found it by just quickly, easily just typing INV. So if I want the inverse of all the other ones, INV E4, for example, then we can find that a lot quicker. So that means if I take the inverse of E1 times the inverse, this is long, of E2 times the inverse of E3, and then keep going until how many? 8? 4 times inverse of E5 times inverse of E6 times inverse of E7 times inverse of E8 What do you think we're going to get? What? It does, because multiplication. What should we get? We should get our original matrix. That's our original matrix A. So okay. Was this interesting? I was going to have you do it as a worksheet, but I thought if I walk through this in class, then so I'm probably still going to give you a worksheet, but so I have it kind of semi-prepared. But now I don't have to explain all that stuff in the worksheet. I could just give you the problem in the worksheet, and you have to look for E1, E2, E3, and all that. Okay. For 3x3, 4x4, a computer would be really important. But now that you know the theory behind this, you should be able to do 2x2 by hand. Because multiplying 2x2 matrices is fairly easy, and finding the elementary row operations of a 2x2 matrix is really pretty basic also. Okay. So just so you know, I have given a problem like that in an exam in the past, where you're supposed to find the elementary matrices and then come up with a way to express the inverse and to express the original matrix A. All right. Now, in practice, this isn't the way we find inverses. Because imagine having to find all these elementary matrices, collect them somewhere, and then later multiply them all out. Okay. So what we're probably more interested in is the process of coming up with this matrix, the identity matrix. And some of you probably know the idea already of how to do this, but let's talk about it. Let's say we want to find, I'm going to go back to Matlab, and let's say we want to find this matrix A. What we do sometimes is that we attach an identity matrix next to it. So instead of having a 3x3 matrix, you will have a 3x6 matrix. Yeah, and then so the second part of that matrix will be the identity. So I'm going to call this matrix B in Matlab, and I can easily kind of augment this matrix with the identity. So now instead of having a 3x3 matrix, I have a 3x6 matrix where the last three columns are actually the identity, is actually the identity matrix, right? So once you have this, you would go through the same elementary row operations that got you. Essentially, what you want to do is you want to make your first three columns the identity. So you're going to shrink this, and then you're going to perform the same row operations. Does that make sense? So I would say I would multiply the first row by -5 and add it to the second row. But I would do that all the way across, not just the first three columns, but I would do that to the other ones. Okay? Now, you would do this by hand, but since we have it all defined already, right? We have it all defined already. Let's take a look at E1 times B. So if you take a look at E1 times B and you look at the last three columns, you'll see that that's just E1, right? Now let's do E2 times E1 times B. So I'm essentially doing the elementary row operations to this new augmented matrix. So this is what happens when you multiply that, right? Let's do a couple more. E3 times E2 times E1 times B. So this is a row swap, I think, right? So it looks like we row swapped. Let's do one more. E4 times E3 times E2 times E1 times B. Oh, this one, I shrunk my screen, but yours should have, if you're on full screen, then you should have all 6 columns. But here, I split my columns. All right. Okay, so let's cut to the chase here and just do the whole thing. We went all the way to E8. I'm just going to look for it. This is good enough. So E8 times E7 times E6 times E5 times E4 times E3 times E2 times E1 times B. Now let's take a look at the result. So the result is your matrix A turns into the identity, and then you have some other matrix that's on the other side of that, which used to be the identity, is now equal to something. Guess what that something is? So the inverse of A is in those last 2 elements. Yeah? For 2 by 2, yeah, but for 3 by 3, no. Not for a 3 by 3 matrix. I mean, I'm almost positive that you can't, but then there might be some formula somewhere that people use. So the basic idea is to have you write your matrix next to the identity matrix. And then when you do these row operations, imagine doing the row operations on A to get the identity. And what you're essentially doing is you're also multiplying the identity times all those things. So if you're doing the E1, E2, all the way up to whatever we had, let's do EJ, on this matrix, you're actually doing it on both matrices, even though they look like it's just one big matrix. You're actually doing it on both matrices at the same time. When you do this operation, on the left-hand side, you're going to get EJ, not the left-hand side. On the left side of your augmented matrix, you're going to get EJ times E whatever times E2 times E1 times A. And then over here, you're going to do the same thing to the I, the identity element, EJ, E2, E1 times I. Luis, I finally got this I in the right spot, and you kept on asking about that. So this is really what's happening, right? And this, we said, was the identity, A inverse. A inverse times A is the identity. And then this, well, that's A inverse, like we said. A inverse times identity is A inverse. So that algorithm is really relying on the basic elementary row operations. And if you do that with A, making that into the identity, and you do that to the identity at the same time, you're eventually going to get A inverse. Right? Row equivalent means you can do basic row operations to make it look like the identity. If for some reason you knock off a whole row of zeros or 2 rows of zeros, then it's not row equivalent to identity because you need the ones and all the diagonal. Yeah. Okay. So to find the inverse of a 2 by 2 matrix, let's use that formula where we find the determinant, and then you flip the diagonals, negative the wings. That's easy. But for anything else that's larger than that, like 3 by 3, 4 by 4, 5 by 5, oh my goodness, then you should be able to find the inverse using this particular method. Yeah. I don't think I'm going to restrict to as few row operations as possible. You can row reduce any way you want. But when you do, then you have to keep track of your elementary matrices for some of the problems that I'll be asking you. Yeah. Okay. Any other questions? All right. Yes. And in an exam situation, it'll just probably be a 2 by 2 matrix. And so to make any 2 by 2 matrix into the identity, it's really fairly quick because you only have a handful of steps to make that. A 3 by 3 matrix is a little bit more difficult, and 4 by 4 is really hard. But for 2 by 2, it should be fairly easy. You shouldn't have more than 5 elementary matrices for that. All right. Yeah, and if you do have more than 5 elements for row reducing a 2 by 2 matrix, then yes, something's wrong. Okay. So now that you know how to find the inverse of a matrix, invertible, invertible. So the ideas behind finding the inverse of the matrix isn't just for the sake of finding the inverse of the matrix. It turns out that if you can find the inverse of the matrix, there's a whole slew of things that comes with that. And what happens here is that in this particular theorem, called the invertible matrix theorem, part 1, is that you have 12 equivalences. What that means is that if one of them is true, then every single one of the other ones are also true. It's all or nothing. If one of them is false, then the rest of these are false. And this goes through L, and after we learn a few more things later on, it's going to go up to like T or W or something like that, because we're going to add on to this list. No, this isn't worth memorizing. I was going to say it'll become obvious, but maybe not. You'll find links to this. We'll see. Luis? Well, if the main motivation was to be able to solve for AX is equal to B. So you just take the inverse, so x is equal to A inverse times B. That's one of the main motivations. But aside from that, it turns out that there's a whole bunch of other important things that come along with it. So let me just read through this. If A is an invertible matrix, then A is row equivalent to the identity. Randall asks, what's row equivalent to the identity mean? It means you have to, after row reducing, you can get the identity at the end. And if you get a row of zeros, then it's not row equivalent. If you do these row reducing, you get a row of zeros, then it's not invertible because it's not equivalent, row equivalent to the identity matrix. Yes, it would have more than the trivial solution for a homogeneous. Yeah. Also have linear dependence. See, all that seems obvious. Well, I don't know about obvious, but all that seems like those are the things that kind of make sense to us, right? Because we've had information about what it means to have only the trivial solutions and what that means to only, if it only has the trivial solutions, then it's all linearly independent. So now the inverse theorem puts it all together, saying that if it is linearly independent, then you only get the trivial solution. And then now there's a whole bunch of other things. So row equivalent, it has n pivot positions, but we know that for being row equivalent or being able to reduce. The equation, the homogeneous equation only has a trivial solution. The columns of A are linearly independent. The linear transformation is one-to-one. So that's a little bit new. We didn't really talk about one-to-one and onto. That's an important topic in linear algebra that we're kind of skipping, glossing over. And so if we had more time, I think we're talking about linear transformations, we would dig into the idea of what it means to be one-to-one and onto. But in this case, it's the one-to-one-ness that makes it invertible. The equation AX equals B has at least one solution. The columns of A span all of Rn. So it spans everything in Rn. The linear transformation maps onto, so it's one-to-one and onto. The n by n matrix C, there exists a C such that C times A is equal to I, and there exists a D. So all this is saying that C in point number J and then D in point number K are just the inverses. So we just call that A inverse. And then the transpose is also invertible. Yeah. A inverse. So C equals A inverse and D equals A inverse. So they're just they're not giving it a name, but it's really A inverse for both of them. And the idea behind the inverse, remember, is that you can multiply it on the left and on the right, or you can multiply it on the left or on the right, and you would still get the identity. And that's what they're doing here. Yeah, they're multiplying C on the left and they're multiplying D on the right, but it's the same thing. Call it A inverse. Say it again. Yeah, C could be D. D. I mean, I think for the sake of having more bullet points, they separated this into two different things where it could have just been set into one, because that's how the definition of inverse is. You multiply it on the left and you multiply it on the right, you get the identity. So here they separated it for some reason. And
J and K is basically saying that the property applies
to the inverses. Inverses times the original matrix. Now, in this section, they prove things. And the way to prove this is that you're supposed to prove one to another and then prove, you prove all the way down that one applies to the other, and then you prove it all the way back. The way the proofs work is that you have to assume if the one thing is true, then you have to prove the next statement. And then if that statement is true, then you have to prove the next statement. But the way they did it is a little bit differently. They proved it, and they proved a subset of it or something like that, and they proved connections to the others, and then they tied it all in. And so if and only if proofs for math majors, you have to prove one way or the other. But if you have a string of them, you can just loop them up. I don't know if you guys know what I'm talking about, but I'm not going to prove them because that's a lot of work. You can look in the book. But I wasn't planning to ask you the proofs on the test anyways, but this is from section 2.3. So now that we know how to find inverses, these are the ramifications for having inverses, and it ties into a lot of stuff that we discussed. And then when we learn more things about matrices, we're going to add on to this list. All right. All right. I don't know if I had any particular problems to pick out. I do want to point out that when they're talked about linear transformations, they talked about in two different spots. But again, this is one of those things that they probably could have put together into one bullet point. That if you have a linear transformation, if the inverse, if the matrix is invertible, then the corresponding linear transformation is one-to-one and onto. Think about one-to-one and onto. Think about the parabola, right? The parabola is not a one-to-one function. But if you cut that in half and just take a look at half of this, now it becomes a one-to-one function, right? The original parabola doesn't pass the horizontal line test, so it's not a one-to-one function. But if you cut it in half, now it passes the horizontal line test. Now you can find the inverse of that. And the inverse of the parabola is a square root function. It's like that. And if we restrict our domain and range to just the positive real numbers in x and positive real numbers in y, then you can say it's one-to-one and onto. So I don't know how many of you guys are familiar with that one-to-one and onto terms, but that's what they're saying about linear transformations. Okay. So I don't know if this was a lot of information. We did most of our stuff today on Matlab just to show you the importance of the elementary matrices. And then there's a lot of theory behind that, the inverse functions or the inverse matrices here in this section. So I'm going to see if I can. I'm going to make up that worksheet for you guys to find elementary matrices for some 4x4 matrix or something like that, and then have you guys work on it in MATLAB, so that when it comes time for the test where you have to do something for a 2x2 matrix, hopefully it'll become easier for you. Any other questions? Yes. Maybe. Was it a transformation problem or an actual word problem? Okay. Yeah. So I don't know if we're going to do that in class. I think I said I was going to try to make videos of some of the applications. So I'll see if I can come back to that idea, and then I'll let you know if it's up. All right. Good luck.